Welcome to this RSET online session. I am Dr. Rinku Jacob from the Department of Basic Sciences and Humanities, Rajagiri School of Engineering and Technology. The topic of my lecture for today is quantum mechanics, and this is the second part of my lecture series on this topic. This topic is from the first part of Module 3 in the Engineering Physics syllabus for first year engineering students of Circuit branch as per the KTU syllabus 2019. These are the topics I plan to discuss in this session. These are some of the questions taken from the previous university question paper related to the topic quantum mechanics. In classical mechanics, Newton's second law, that is F equal to ma, is used to make mathematical prediction of the path a given physical system will take over time following a set of non-initial conditions. On solving this equation, we get the position and momentum of the physical system as a function of the external force F on the system. And position and momentum parameters are sufficient to describe its state at each time. In quantum mechanics, the analog of Newton's law is Schrodinger equation. The concept of wave function is a fundamental postulate of quantum mechanics. It is to be noted that in quantum mechanics, the wave function defines the complete state of a quantum mechanical system at each spatial position and time. So solutions to the Schrodinger equation describe not only molecular, atomic and subatomic systems, but also macroscopic systems, possibly even the whole universe. Now we look onto the one-dimensional Schrodinger equation. Here we consider a particle moving along the positive x-axis with energy E and momentum P. Then the wave function for this particle at a given spatial position x and at a time t is given by psi equal to a exponential minus I by h cross et minus px. Now we differentiate equation 1 with respect to time t. Here we are taking the partial derivative because the wave function depends on two independent variables, that is position x and time t. That is dou psi by dou t equal to dou by dou t of a exponential minus I by h cross into et minus px. Since a is constant, it is taken outside. So dou psi by dou t equal to a into dou by dou t of exponential minus I by h cross into et minus px. Now when we take the derivative of the bracketed term, we get dou psi by dou t equal to a into exponential minus I by h cross into et minus px into dou by dou t of minus I by h cross into et minus px. That is dou psi by dou t equal to a into exponential minus I by h cross into et minus px into minus I e by h cross. Here a exponential minus I by h cross into et minus px is the wave function psi itself. So we write dou psi by dou t equal to minus I e by h cross into psi. That is equation 2. Now multiplying the numerator and denominator of the RHS by the complex number I. That is dou psi by dou t equal to minus I by I into I e by h cross into psi. That is dou psi by dou t equal to minus of I square by I into e by h cross into psi. But I square is negative 1. So dou psi by dou t equal to minus of minus 1 by I into e by h cross into psi. Or dou psi by dou t equal to 1 divided by I into e by h cross into psi. That is dou psi by dou t equal to e by I h cross into psi. By taking I h cross onto the other side, we get e psi equal to I h cross into dou psi by dou t. That is equation 3. Now we use the wave function of the particle which is given by equation 1. Differentiate the wave function twice with respect to the position coordinate x. That is dou psi by dou x equal to dou by dou x of a exponential minus I by h cross into et minus px. That is dou psi by dou x equal to a into exponential minus I by h cross into et minus px into dou by dou x of minus I by h cross into et minus px. When you take the derivative of the bracketed function, we get dou psi by dou x equal to a exponential minus I by h cross into et minus px into I p by h cross. Now to take the second derivative, we differentiate again with respect to the position coordinate x. That is dou square psi by dou x square equal to dou by dou x of I p by h cross into a into exponential minus I by h cross into et minus px. that is dou square psi by dou x square equal to ip by h cross into a into exponential minus I by h cross into et minus px into dou by dou x of minus I by h cross into et minus px. That is dou square psi by dou x square equal to ip by h cross into a into exponential minus I by h cross into et minus px into ip by h cross. So there are two terms ip by h cross. So it becomes dou square psi by dou x square equal to I square p square by h cross square into a exponential minus I by h cross into et minus px. Now I square is minus 1. So the equation reduces to dou square psi by dou x square equal to minus p square by h cross square a exponential minus I by h cross into et minus px. Here a exponential minus I by h cross into et minus px is the wave function psi. So dou square psi by dou x square equal to minus p square by h cut square into psi. On taking h cross square to the other side of the equation, we get p square psi equal to minus h cut square into dou square psi by dou x square, which is equation 4. Using equation 3 and 4, we can find the total energy of the particle. The total energy of the particle is the sum of the kinetic energy and potential energy. That is E is equal to P square by 2m plus V, where P square by 2m is the kinetic energy and V is the potential energy and E is the total energy. Now to make use of equation 3 and 4 in the total energy equation, we multiply both sides of the total energy equation by the wave function psi. That is E psi equal to P square psi by 2m plus V psi. Using equation 3 and 4 in the energy equation, we get I h cut dou psi by dou t equal to minus 1 by 2m h cut square into dou square psi by dou x square plus V psi. This is the one-dimensional time-dependent Schrodinger equation. Now we move on to the case of one-dimensional time-independent Schrodinger equation. In a number of cases, the potential energy V of a particle does not depend on time but depends only on the position of the particle. In such cases, the wave function psi, which is a function of both position and time, should be written as a function that independently shows the position information and time information. For that, we write the wave function as psi is equal to a into exponential minus I et by h cross into exponential I px by h cross. That is psi is equal to psi 0 exponential minus I et by h cross. That is equation 1. Where psi 0 equal to a exponential I px by h cross. That is equation 2. Now we differentiate equation 1, that is the modified wave function with respect to the position coordinate x. That is dou psi by dou x equal to exponential minus I et by h cross into dou psi 0 by dou x. Differentiating again, that is for the second time, we will be getting dou square psi by dou x square equal to e raised to minus I et by h cross into dou square psi 0 by dou x square. That is equation 3. Now we differentiate the modified wave function which is given by equation 1 with respect to the time coordinate. That is dou psi by dou t equal to psi 0 into dou by dou t of exponential minus I et by h cross. That is dou psi by dou t equal to psi 0 into minus I e by h cross into exponential minus I et by h cross. Now we have the equation for dou square psi by dou x square as equation 3 and dou psi by dou t as equation 4. Now using these values in the time dependent Schrodinger equation which is given by I h cut dou psi by dou t equal to minus 1 by 2m h cut square dou square psi by dou x square plus V psi. We get I h cross into minus I e by h cross into psi 0 into exponential raised to minus I e t by h cross equal to minus h cross square by 2m into exponential minus I e t by h cross into dou square psi 0 by dou x square plus V psi 0 into exponential minus I e t by h cross. Now dividing throughout by exponential minus I e t by h cross, we get I h cross into minus I e t by h cross into psi 0 equal to minus h cross square by 2m into dou square psi 0 by dou x square plus V psi 0. That is minus I square e into psi 0 equal to minus h cross square by 2m into dou square psi 0 by dou x square plus V psi 0. Since I square equal to minus 1, the above equation reduces to E psi 0 equal to minus h cross square by 2m into dou square psi 0 by dou x square plus v psi 0. Now taking v psi 0 to the other side, we get e psi 0 minus v psi 0 equal to minus h cross square by 2m into dou square psi 0 by dou x square. Now multiplying both sides of the above equation with 2m by h cross square, we get 2m by h cross square into e minus v into psi 0 equal to minus h cross square by 2m into 2m by h cross square into dou square psi 0 by dou x square. The 2m by h cross square and h cross square by 2m will be cancelling on the RHS. So we get 2m by h cross square into e minus v psi 0 equal to minus dou square psi 0 by dou x square. Now on rearranging, that is taking all the terms to the LHS, we get dou square psi 0 by dou x square plus 2m by h cross square into e minus v psi 0 equal to 0. This is the time independent Schrodinger equation in one dimension. Now Schrodinger time independent equation in 3 dimension is given by del square psi 0 plus 2m by h cross square into e minus v into psi 0 equal to 0, where del square equal to dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Now we discuss about the conditions that should be satisfied by a wave function that represents a particle before we use the wave function into the Schrodinger equation. And these conditions are called as admissibility conditions. Firstly, the wave function psi should be finite and should tend to 0 when x tends to plus or minus infinity. Secondly, psi should be single valued at every point. Thirdly, psi, dou psi by dou x or dou square by dou x square, etc. should be continuous. That means the derivatives should be continuous at each point. Now we deduce the expression for energy and wave function of a particle trapped inside a one-dimensional infinite square well potential. For that, we assume a particle is trapped inside a potential well. Here the particle is allowed to move only along x-axis. The y-axis is the potential applied externally. The particle can move through x-axis if its kinetic energy is more compared to the potential energy it faces. So at the origin x equal to 0 and at a distance away from the origin, say at x equal to L, the potential is infinity. That means the particle can never cross or stay at x equal to 0 and at x equal to L due to infinite potential it faces. So the particle is trapped in between x equal to 0 and x equal to L. Otherwise we say the particle is trapped in a potential well. Inside the well, that is in the region between x equal to 0 and x equal to L, there is no restriction for the motion of the particle as the potential V is 0. Now to study the dynamics of this particle trapped inside this well, we make use of the Schrodinger time independent equation, which is given by dou square psi by dou x square plus 2m by h cross square into e minus v into psi equal to 0. But inside the well, as the potential is 0, we take v equal to 0. So the time independent Schrodinger equation reduces to dou square psi by dou x square plus 2m by h cross square into e psi equal to 0, which is equation 1. Now we substitute 2m e by h cross square as k square. So we get dou square psi by dou x square plus k square psi equal to 0. That is equation 2. And the value of k square equal to 2m e by h cross square is taken as equation 3. So equation 2 is a standard form of differential equation. The general solution of this equation is psi equal to a exponential ikx plus b exponential minus ikx, which is given as equation 4. So this is the expression for the wave function that represents the trapped particle inside the potential well. Now we have to find the unknown terms in the equation, that is a and b. For that we take the boundaries of the motion of this particle. In the figure it is clear that the particle cannot exist at the points x equal to 0 and at x equal to L. That means as the particle is not present at these points, the wave function should be 0 at x equal to 0 and at x equal to L, because the modulus square of the wave function is the probability density. So we first take the boundary x equal to 0, and here as the particle cannot exist, definitely psi will be 0. Now applying this condition to the wave function representing the particle, that is equation 4. On LHS it is 0 as psi equal to 0. On RHS, in both terms the exponential to the power 0 becomes unity. So we get 0 equal to a plus b or b equal to minus a. Now we obtain the relation between the unknown quantities a and b. So using the value of b equal to minus a in equation 4, we get psi equal to a exponential ikx minus a exponential minus ikx. Now taking a as common, we get psi equal to a into exponential ikx minus exponential minus ikx. Now we make use of the relation sin x equal to exponential ix minus exponential minus ix by 2i. On taking 2i to the other side, we get exponential ix minus exponential minus ix equal to 2i sin x. Now to apply this result in our derivation, we consider exponential ikx minus exponential minus ikx equal to 2i sin kx. So we can write psi equal to 2ia into sin kx. We can take 2ia as a constant c. So we get psi equal to c into sin kx, which is equation 5, where c equal to 2ia. Now we have to find the value of c in equation 5. For that, we take the second boundary, that is at x equal to L. Here, as the particle cannot exist, the wave function psi is 0. Now applying this condition to equation 5, we get 0 equal to c sin kl. As c is not equal to 0, definitely sin kl should be 0. For a sine function to be 0, the angle should be an integral multiple of pi. That is, for sin kl to be 0, the angle kl should be equal to n pi, where n equal to 0, 1, 2, etc. So k is equal to n pi by L, which is equation 6. Now using the value of k given by equation 6 in the equation 5, which is the equation for wave function, we get psi equal to c sin n pi x by L, which is equation 7. Now to find the value of c, we apply the normalization condition. Here the normalization condition is that we sum the probability of finding the particle between x equal to 0 and x equal to L. As we are calculating this probability continuously between x equal to 0 and x equal to L, we use integration instead of summation. So integral of probability density, that is modulus square dx, in the interval from x equal to 0 to x equal to L is equal to unity. This means as the particle is definitely present in the region between x equal to 0 and x equal to L, the sum of probability of finding the particle in this range between x equal to 0 and x equal to L is definitely unity. Now we use the value of wave function given by equation 7 here. So we get integral of c sin n pi x by L all square into dx equal to unity within the limit x equal to 0 to x equal to L. Now taking c square outside as it is a constant, then c square integral 0 to L sin square n pi x by L into dx equal to 1. Since we cannot directly integrate the sine square function, we make use of the relation cos 2 theta equal to 1 minus 2 sine square theta. Or we can write sine square theta equal to 1 minus cos 2 theta all divided by 2. So the sine square term in the integral can be replaced by this formula. So we write c square by 2 integral within the limit 0 to L 1 minus cos 2n pi x by L into dx equal to 1. Or c square by 2 integral 0 to L dx minus integral 0 to L cos 2n pi x by L dx equal to 1. Now c square by 2 integral dx within the limit 0 to L is x within the limit 0 to L minus integral of cos 2n pi x by L into dx within the limit 0 to L is sin 2n pi x by L all divided by 2n pi by L within the limit 0 to L, that is equal to 1. Now applying upper limit minus lower limit to the first term, that is L minus 0. Now applying upper limit minus lower limit to the second term, that is sin 2n pi L by L by 2n pi by L minus sin 2n pi into 0 by L all divided by 2n pi by L equal to 1. Now the first term in the bracket becomes sin 2n pi divided by 2n pi by L, and the second term becomes sin 0 divided by 2n pi by L. Now sin 2n pi is 0 as we put n equal to 1, 2, 3, etc. So the first term and second term inside the bracket becomes 0. So we get c square by 2 into L equal to 1. So c is equal to square root of 2 by L, which is equation 8. Now we take the wave function representing the trapped particle inside the potential well, which is given by equation 7. Now using the value of c derived into the wave equation, we get psi equal to root of 2 by L sin n pi x by L. This is the equation representing the wave function for the particle trapped inside the well. Now we find the expression for the allowed energy for the trapped particle inside the well. For that we take the value of k from equation 6, that is k is equal to n pi by L. Now squaring on both sides of the equation, we get k square equal to n square pi square by L square. Now we make use of equation 3, that is k square equal to 2me by h cross square. Comparing the RHS of both equations which have k square on LHS, we get 2me by h cross square equal to n square pi square by L square. Now writing in terms of the energy, we get E is equal to n square pi square h cross square by 2mL square, where n equal to 1, 2, 3, etc. This equation shows that the energy possessed by the trapped particle inside the well is quantized. It cannot take continuous values of energy. The allowed energy for the particle is given by this equation. Now we try to plot the allowed energy levels of the particle trapped inside the one-dimensional potential well. If the mass of the particle and the width L of the potential well is not changing, then the energy is proportional to n square. So when we put n equal to 1, we get E1 equal to pi square h cross square divided by 2mL square. This is the minimum energy possessed by the trapped particle inside the well. Otherwise, we say it is the ground state energy. Now when we put n equal to 2, the equation gives E2 is equal to 2 square pi square h cross square by 2mL square. That is, the next possible energy allowed for the trapped particle is 4 times the ground state energy. Similarly, when we put n equal to 3, we get the next possible energy E3 as 9 times the ground state energy. And if we put n equal to 4, we get 16 times the ground state energy. When we plot it, we get the allowed energy levels for the trapped particle inside the potential well. Now we discuss about the topic quantum mechanical tunneling or simply quantum tunneling. In classical mechanics, if a particle is approaching a barrier or a wall with kinetic energy less than the potential of the barrier, then the particle cannot go through the wall and it gets reflected. But in quantum mechanics, when we take subatomic particles like electron, proton, neutron, etc., its de Broglie wavelength is comparable for its measurement. So we treat the particles as not a particle but as a wave. And this wave is mathematically expressed as a wave function of the particle. In this case of subatomic particles, it is observed that even if the kinetic energy of the particle is less than the barrier potential, the probability of finding the approaching particle towards the barrier disappears and appears on the other side of the barrier without any flow through the well. This phenomenon is called as quantum mechanical tunneling. But in classical mechanics, this is not possible. Quantum tunneling plays an essential role in several physical phenomena such as the nuclear fusion in the stars that include our sun. It has important applications in tunnel diode, in quantum computing, and in scanning tunneling microscope. The animation shown here shows a particle as a wave packet of mean energy of 14 that advances towards a barrier having potential of 20. So after it hits the barrier, a very small portion is transmitted to the other side of the barrier through the phenomenon of tunneling. The rest of the wave is reflected back from the barrier. So in our analysis, we have to study about 3 different waves. One is about the incident wave, then about the reflected wave, and finally about the transmitted wave. Now for our analysis, we divide the picture into 3 regions. The region where the incident particle approaching the barrier is named as region 1. The region inside the potential barrier is named as region 2. And the region on the other side of the barrier is named as region 3. So for quantum mechanical analysis, we see the matter wave or probability wave is approaching the barrier in region 1. On hitting the barrier, which is having potential greater than the energy of the approaching particle, some portion of the wave is reflected back into the region 1 and some portion tunnel through the barrier, that is region 2, and reaches the region 3, which is the other side of the barrier. How much portion of the incident wave actually tunnels through the barrier depends on the width of the potential barrier, the potential of the barrier, the mass of the particle, and the energy of the particle. If the potential of the barrier is infinity, then there will not be any tunneling through the barrier. To study quantum mechanically the dynamics of the particle that is approaching the barrier, we make use of the Schrodinger equation. For that, first we have to represent mathematically the waves traveling through the region 1, that is incident and reflected waves. Then the wave that tunnel through the region 2 and the wave that is transmitted to the other side of the barrier, which is the region 3. So let us write the wave function of the particle in region 1 as psi 1 and that in region 2 as psi 2 and in region 3 as psi 3. From the figure, it is clear that the wave function in region 1, that is psi 1, will contain information about the incident and reflected waves from the barrier. And the wave function in region 3, that is psi 3, will contain only the information about the transmitted wave, as there is no reflected wave in region 3. Now we write the time-independent Schrodinger equation for the particle wave in region 1. As the potential is very small or nearly zero in region 1, we take V to be a 0. So we write dou square psi 1 by dou x square plus 2m by h cross square into E into psi 1 equal to 0. That is equation 1. Now we write the time-independent Schrodinger equation for the region 2. That is dou square psi 2 by dou x square plus 2m by h cross square into E minus V into psi 2 equal to 0. That is given by equation 2. In region 2, we write E minus V as the potential in this region is non-zero. And finally, we write the time-independent Schrodinger equation for the particle in region 3, that is for the transmitted particles through the barrier. In this region, as the potential is very small or zero, we take the potential V to be as 0 in the Schrodinger time-independent equation. So we write dou square psi 3 by dou x square plus 2m by h cross square into E psi 3 equal to 0. That is equation 3. The time-independent Schrodinger equation given by equation 1 and equation 3 are of the standard form of differential equation given by d square y by dx square plus k square y equal to 0. And the solution for this equation is given by y is equal to a exponential ikx plus b exponential minus ikx. So the solution for the equation 1 and equation 3 can be written as psi 1 equal to a exponential ik1x plus b exponential minus ik1x, that is equation 4. And the solution to the equation 3 is psi 3 equal to f exponential ik1x plus g exponential minus ik1x, that is equation 5, where k1 equal to square root of 2me by h cross square. In equation 4, a exponential ik1x represents the incident wave and b exponential minus ik1x represents the reflected wave from the potential barrier in the region 1. Similarly, in equation 5, f exponential ik1x represents the transmitted wave to the region 3 and g exponential minus ik1x represents the reflected wave in region 3. Here, a, b, f and g indicates the amplitude of the corresponding waves. As I explained in equation 4, a exponential ik1x represents a wave of amplitude a incident from the left of the barrier and b exponential minus ik1x represents the reflected wave from the barrier. Now we look into equation 5. This is the wave function for the particle in region 3. On the right side of the barrier, only transmitted wave is there. And in equation 5, f exponential ik1x represents the transmitted wave. As there is no reflected wave, the second term in the equation should vanish. As exponential ik1x cannot be 0, the only possibility is that g should be 0, where g is the amplitude of the reflected wave. As there is no reflected waves in region 3, the amplitude representing the reflected wave, that is g, should be 0. So equation 5 reduces to psi 3 equal to f exponential ik1x, that is equation 6. Now we look at equation 2, which is the Schrodinger equation for the particles in region 2. As the potential of the barrier is more compared to the energy of the particle, we take a negative sign from the second term and write the equation as dou square psi 2 by dou x square minus 2m by h cross square into v minus e into psi 2 equal to 0. That is equation 7. The solution of equation 7 is psi 2 equal to c exponential minus k2x plus d exponential k2x, that is equation 8. Here we use k2 instead of k1 as there is an additional term v, which is the potential of the barrier. So k2 equal to root of 2m v minus e by h cross square. As there is no complex number in the exponential terms in equation 8, that is the exponents are real. So we cannot express it in terms of sine or cosine, or there is no harmonic terms. So psi 2 does not oscillate. As you can see in the region 2, there is no oscillations in that region. There is an exponential variation. Now we find the transmission probability. Transmission probability is the ratio between the probability of finding the particle in the region 3 to the probability of incident particles hitting the barrier from region 1. That is T equal to f star by a star, or it is equal to modulus of f square divided by modulus of a square, where f is the amplitude of the transmitted waves to the region 3 and a is the amplitude of the incident wave in region 1. Now the transmission probability can also be expressed in terms of the energy of the incident particle, potential of the barrier and width of the barrier, and it is given by T equal to 16 e into v minus e by v square into exponential minus 2k2l. This is the end of part 2. Thank you for watching this RSET online video session on the topic quantum mechanics. For more lectures, please visit the link shown below.